So this is the first of at least a couple of videos that are going to look at graphs of rational functions. A rational function is a ratio, any function that can be written as a ratio of two polynomial functions would be one way of putting it. Rational expressions kind of play the same role regarding polynomials that rational numbers play regarding integers. So what I mean by that, if you look at the integers 0, 1, 2, 3, 4, and so on, -1, -2, -3, and so on, those are the whole numbers or integers. Probably don't need a special name for whole numbers as opposed to integers, but the whole numbers usually exclude the negatives. Could debate that, whether we need all these words for what we're dealing with. But anyway, the integers, -1, -2, -3, all the way to -infinity, 0, 1, 2, 3, 4, and so on. And I find that a lot of students, even calculus students, don't necessarily have a firm grasp in their mind of exactly what the integers are. Anyway, if you take an integer and divide it by an integer that's not 0, then you're dealing with a rational number, pretty much what we just mean by fractions when we use the term fraction. Well, polynomials are kind of like the integers. They make what mathematicians call a ring, which means you can multiply and add and subtract and that sort of stuff, but you can't necessarily divide with two polynomials and get a polynomial. The rational expressions are a larger thing. They make up a more interesting set in that you can actually do division there, and if you divide a rational expression by a rational expression, you get a rational expression. Anyway, maybe at some point we could talk about that some more, but interested here in just graphing a few of them. Now, this first one makes sense. Probably the simplest rational expression is to take like the simplest number 1 and divide it by the simplest non-constant polynomial x, 1 over x, 1 divided by x. The fraction with a numerator of 1 and a denominator of x, those all mean the same thing. It's also written sometimes in terms of exponent notation. Negative exponents mean reciprocals. X to the negative first is the same thing as the reciprocal function of 1 over x. So you should be familiar with this. It has two branches. It makes up what's called a hyperbola. We'll, at the end of the term, look at hyperbolas in more generality. So this hyperbola has two branches to it, one in the first quadrant, one in the third quadrant. In the first quadrant, both x and y are positive. In the third quadrant, both x and y are negative. And it only exists in those quadrants. It does not exist in quadrant 2, does not exist in quadrant 4. Because to get into those quadrants, it would have to cross either the y-axis or the x-axis. When I say it, I mean the graph or the function itself, the graph of the function, to be more precise, technically correct about the whole business. Well, it turns out that as x gets larger and larger, if we're moving from, let's say, x equals 0, come back to that moment, all the way out to x equals infinity. Of course, it never actually equals infinity, it approaches infinity. Well, as that happens, the whole thing, 1 divided by x, is going to get smaller and smaller. You can see that here, and you should be able to think about it and convince yourself this behavior continues. If x is 1, y is 1. X is 2, y is 1/2. X is 3, y is 1/3. X is 4, y is 1/4, and so on and so on. As you keep dividing by larger numbers, it gets smaller and smaller. I sometimes think of this as like the pizza party function. If you have one pizza and x is the number of people at the party, well, how much pizza each person gets depends on how many people are there. If you have one person, well, congratulations. Nobody came to your party, but you get the whole pizza. 2 people, half a pizza. 3 people, 1/3 of a pizza, so on. Assuming fair distribution, which mathematics assumes all kinds of unreasonable things like that. If you approach negative infinity, we'll just jump over 0 here and come back to that moment, but if you head off in this direction, to the left, well, you have 1 divided by a negative number, similar sort of behavior. If you're just looking at the absolute value, it's going to be the same thing I was talking about before, 1/2, 1/3, 1/4, and so on. However, if x is a negative, well, positive divided by negative is negative, so since we have 1 divided by negative numbers, it's going to stay here in negative territory. Well, how about 0? Well, as you already know, you can't divide by 0, so we can't plug 0 in here. So there's a break, a gap between the two branches going from left to right. It also leads to a break going up and down. One way of thinking about that, if you're to set this to 0, if I were to go ahead and take my function here, f of x equals 0, just throw in that for purposes of illustration for a moment. I think I'll take it away shortly. If f of x is equal to 0, well, 1 over x equals 0. You could solve that equation mentally by multiplying both sides of the equation by x. If you multiply both sides of the equation by x times 1 over x is just 1. And no matter what x is, x times 0 has to be 0. So the only way that this equation has a solution is if 1 equals 0. Well, 1 doesn't equal 0, so there is no solution. Since there is no solution, shouldn't even write down such an ugly equation. It turns out not only can x not be 0 here, but also y, or f of x, cannot be 0 in this case. So there is no x-intercept, there is no y-intercept. The y-intercept would be x equals 0. Well, can't have that. And there's also no x-intercept because that would mean y equals 0. I'm not sure if I just said that right or if I switched x and y around, but think about it in your own words. And if my words seem wrong, well, fix them. Try not to make mistakes, but sometimes they do. Okay, anyway, this is the picture. Now, if you're to look at this from a distance, zoom out, if the axes are turned on, you wouldn't even see the graph because it's so close to the axes. We call these asymptotes. There's a vertical asymptote, which is the y-axis. There's also a horizontal asymptote, which is the x-axis. Asymptote, for our purposes here, means that the graph gets really close to those lines. For right now, our asymptotes are lines. And it's approaching this straight line coming down this way. If you were to follow the green curve this way, it approaches that. And if you looked at it from a distance, all you would see would be the asymptotes. This little bump here, this little bump here, become almost irrelevant. Okay, so that's really all there is to that. It's not a very exciting function, maybe a bit more exciting than some polynomials because it's discontinuous, at least in that 1 point where x equals 0. But in other words, the domain is all real numbers except for 0. You could write that as the union from negative infinity to 0, leaving 0 out, so that would be all in parentheses, negative infinity, comma, 0, parenthesis. And then you could union that with a similar thing going from 0 to positive infinity. That would be the domain, and turns out to be also the range here. Oh, should also maybe mention that this is obviously an invertible function because it's 1-to-1. It's a function because it would pass the vertical line test. It's also a 1-to-1 invertible function because it would pass the horizontal line test. And if you were to draw a line through all the points where x and y are the same, takes a 45-degree angle with the coordinate system, and fold the graph at that line, what you would see is that this part down here and that part there would coincide, likewise here. So not only is this function invertible, it actually turns out that because of the symmetry about that line, it's its own inverse. 1 over x is its own inverse. That's not the only function that is its own inverse. X is its own inverse. What I mean by that, the function y equals x, the identity function, is its own inverse. How do you undo identity? Well, you don't need to. Identity is identity. The inverse of identity is identity. The inverse of the reciprocal is the reciprocal. There are lots of functions that are their own inverses, but not the time to go any deeper into that. Okay, so what we're going to show is that, or if not show, at least sort of intuit, is that there are lots of functions which amount to being just really transformations of this reciprocal function. So for example, if you look at the function f of x equals 1 over x minus 3, that quantity minus 7, well, you can relate this to the function y equals 1 over x, the x, replacing x with x minus 3 in the denominator of the fraction here would amount to shifting 3 units to the right. And then the minus 7 here would amount to shifting 7 units down. So f of x equals 1 over x minus 3, that minus 7 is the shift of this original function. I actually should have given it a different name if I'm going to refer to both at the same time. That's kind of confusing. Maybe I'll go back and just call this one y for the moment. But it is good practice if you have several different functions going at the same time to distinguish between them in some way. But if you're just working on your own and you're sure you're not going to get confused by it, you can of course get kind of loose with that. But if you're writing up a paper to turn into somebody else, you wouldn't want to be calling both of these f of x. So anyway, this new function, which I can now think of as being a transformation of my previous function y equals 1 over x, is shifted 3 to the right and 7 down. So here's the y side over here. All this stuff is on the x side. The x transformations tend to be backwards of what your intuition might think. What I mean by that is that the minus 3 actually shifts the whole thing 3 units to the right instead of 3 units to the left. But on the other hand, the minus 7 does shift down. If we're on the other side, on the y side, then it would be backwards also. Talked about that a little bit in the previous video. Okay, so we know what the graph should look like, and here it is. If you look at the green curve that we started with, y equals 1 over x, the red curve has exactly the same shape, exactly the same size, so to speak. They're congruent shapes, meaning that you could superimpose one on the other if you could just pick it up and move it. You could move the green curve to the red curve or vice versa. Now, when you look at the graph, they may not appear to be exactly the same size, but they are. But there are sometimes illusions that are created by looking at things just in terms of colors and background, all that. If I took away the axes, that might make it clearer, or maybe it's perfectly clear as it is. Okay, so I mentioned for the green curve, the y equals 1 over x function, that the x and y axes are asymptotes. But when you shift the graph, you also shift any asymptotes. They have to go along with the graph in the same sort of way. So the x axis, which has the equation y equals 0, is shifted 7 units down to y equals -7. So -7, so these are even. The scale on this is taking in the even numbers, so -7 is halfway between -6 and -8 there. Don't know if maybe if I can zoom in on that picture. Does not seem to want to zoom in on that picture. Okay, so where did that work? No. I could make it bigger. Oh. Except if I do that, I'm not sure if you see it anymore. Yeah. Let's see if I can just undo that. Wasn't on the picture I wanted anyway. There we go. Anyway, Can't see it all too well, but this is -6 here, -8 there, -7, of course, is halfway between those. Likewise, we have x equals 3 as a vertical asymptote corresponding to the x equals 0 vertical asymptote that we had for the green function. So x equals 0 is just the y-axis. That was the original vertical asymptote for the green curve, and for the red curve, that's been shifted 3 units to the right. So what I'm trying to say here is that if you keep track of the asymptotes, and if you keep track of where the asymptotes come together, which was here at the 0, 0 point, well, moving those will help you to get a good graph, essentially. Since from a distance it looks really just like the asymptotes, we can see the gap here, but if you were to imagine, or you don't have to imagine, just get a graphing utility of some type, use GeoGebra like I have here, or graphing calculator. If you had that, you could go ahead and zoom out, and if you zoom out, what you'll eventually see is just sort of looks like a red cross from a distance. Okay, so moving on from there. Let's see, not sure why I have that picture there again, but it turns out that you can put this, let me start over with that statement. F of x equals 1 over x minus 3 minus 7. So that was the red curve that we're looking at here. Produced way up here. And I think I'll just take this out of here. I don't know why it's there. At the time of putting this together, it must have made sense to have it there. Okay. F of x equals 1 over x minus 3 minus 7. So again, this is the reciprocal function shifted 3 right, 7 down. We can add these two fractions together to create a single rational expression that is usually the simplified version of this. To do that, we need a common denominator. So that would be x minus 3. So I change 7 to 7x minus 21 over x minus 3 by multiplying 7 times 7x by x minus 3. So, and then of course the denominator of 1 for 7 over 1, multiply that by x minus 3. We can now do the subtraction. 0 minus 7x is negative 7x. And we have 1 minus negative 21, which is positive 22. So negative 7x plus 22 over x minus 3 is the same as this 1 over x minus 3 minus 7 that I start off with. Now the difference is I can see the shifts here in terms of the reciprocal function, but once we get to the negative 7x plus 22, that quantity over the quantity x minus 3, looking at that, we would have no idea really about any sort of shift going on. We still have the x minus 3 down here, but can we really think of applying that to x when there is an x up here also? There must be more going on than just looking at the denominator here. So how would you recover the shifts? How would you figure all that stuff out? Well, the sort of inverse operation of the subtraction of these two terms, putting them together into one fraction, would be to use division. So if you were to take x minus 3 and divide it into the negative 7x plus 22, we could actually recover my original f of x. So if we were to divide it out, x minus 3 divided into the negative 7x plus 22. You could, of course, use synthetic division for this. And then I just wrote it up in terms of ordinary long division. It's pretty simple. X goes into negative 7x, negative 7 times x minus 3 is negative 7x plus 21. And then remember we're subtracting, so negative 7x minus negative 7x is nothing, and 22 minus 21 is 1. Well, what does that mean? That means if you take the original fraction up here and divide it out, what you get is negative 7 plus a remainder of 1, but the remainder has to be written as being over x minus 3 because the remainder is sort of like the new dividend that has to be divided by the divisor. And so if you do that, you get, well, I guess I didn't write it down other than it's right up here. 1 over x minus 3 minus 7. Yeah, it seemed like I had it written down someplace else before, but so one way of looking at this is that it would give us the result of f of x is equal to, so the negative 7 plus the 1. Oh, I need a fraction for that, so let's see. Divided by the x minus 3 dividend, divisor. So this is what I'm saying here. So the negative 7, so after we divide it out, that whole, so this quotient up here, the whole thing that's after the result of the division, negative 7, but there's a remainder. The remainder still has to be divided. If I divide it by x minus 3, we have negative 7 plus 1 over x minus 3. Because fractions are implied divisions, if you use division, you can often analyze the result and figure out more about what you're dealing with. And I'm sure we'll see that in some subsequent video. Now, just generally, so if you go back and look at what we've got here, we have a ratio here of two linear expressions. Linear meaning that you've got x in there, but it's really just multiplication and addition or possibly subtraction going on. If you graph just negative 7x plus 22, that's a line. If you graphed just x minus 3, that's a line. Here I'm taking one linear expression, dividing it by another linear expression. In general, you could write such a thing as ax plus b, very similar to the y equals mx plus b sort of thing. And just picking the next couple of letters in the alphabet after a and b, we get c and d. So ax plus b over cx plus d. If you divide this out, it's a little bit abstract, so it's a good practice on your long division skills if you can do this. Or you can maybe try it with synthetic division, see how that would work for this sort of thing. If you divide it out, we get a quotient of a over c and a remainder, which still has to be divided. The remainder turns out to be bc minus ad, that quantity over c, and then that still would have to be divided by cx plus d. Don't spend too much time worrying about what I wrote down here. If you want to pursue it and see if you can create this yourself through long division, I think that's a good exercise. If you want to just look at it and say, I don't like the way that looks, I don't want to think about it, that's fine also. You won't need this, you don't have to memorize it, you don't need to even write it in your notes, but if you want to and think about it later on, that's fine. There might be some usefulness to this. But basically, there's going to be an easier way of figuring out what the asymptotes of a rational expression are than just looking at this. This will give you the horizontal asymptote, which is the a over c. It doesn't really help too much with the vertical asymptote. And you can actually work out both of those in a very general procedure that will apply not only to functions of this type, but ones where the numerator and denominator might be second degree, quadratic, third degree, things like that. So look at that in a later video. Maybe do another example there. So I'm going to actually just copy that and paste it and change it. So I think I'll take out all that stuff here and change this to something like, let's make it pretty simple, 6, -2. Make that real simple by getting rid of it. And this down here, let's make that 4. And just do a brief analysis of this thing. Don't think I need the equal sign. Okay. So we have a rational expression here of the form ax plus b over cx plus d. If you let a be 6, b is 0, c is -2, d is 4. So I could go ahead and divide this out similar to what I did symbolically here, but we really don't need to. As I mentioned before, what we really want to do is keep track of the asymptotes. The asymptotes are going to shift in a particular way. We could divide it out and see how this thing shifts, but if we can figure out the asymptotes, that's going to do the same thing. It's going to tell us how this graph shifts relative to the graph of y equals 1 over x. Well, it turns out that you can recover the horizontal asymptote here by just comparing the 6 and the -2. So if you go back to the example I had up here before, -7 over 1 turned out to be the horizontal asymptote here of y equals -7. Remember, horizontal lines have equations that say y equals some number, so y equals -7 was the horizontal asymptote for our red curve here. And you can think of that -7 as being created by looking at the -7 in the numerator of the original, which is the lead coefficient of the x, and dividing that by the lead coefficient of the x in the denominator. So the -7 in the numerator, 1 in the denominator. Divide that out, you get -7. Similar thing's going to apply here. If I take 6 and divide it by -2, that will give me the horizontal asymptote in this case. I can actually go and copy my previous work here and paste that right up to this. And blank those out for the moment. Okay, so looking at a rational function, this actually goes beyond rational functions of the type that we have here, but look at this one specifically. If you take the lead coefficient of x here and lead coefficient of x there, as long as they both have the same degree, and they do, they're both first degree, they're both linear, well, you can take this lead coefficient divided by that lead coefficient, that will give me the horizontal asymptote. If the degrees are different, it doesn't work. We'll go into that in some later video. But for now, we have 6 divided by -2. And so I'll put that in here. So in the numerator, -2 in the denominator. And of course, 6 divided by -2 is -3. So if you're comparing this, based on what we've got so far, if you're comparing this to y equals 1 over x, it would shift 3 units down. So the horizontal asymptote for y equals 1 over x is the x-axis, y equals 0. The horizontal asymptote here is 3 units down, y equals -3. The graph will approach that as x approaches infinity. It will also approach that as x approaches -infinity. Okay, how about the vertical asymptote? Well, it turns out that for all rational functions, the vertical asymptote or the vertical asymptotes, there can actually be several of these. Any vertical asymptote is going to correspond to a break in the function, because if it's a vertical asymptote for rational functions, it's going to turn out it doesn't cross the vertical asymptote. It can cross a horizontal asymptote, but it can never cross the vertical asymptote. And that's because the vertical asymptote represents the place where the denominator becomes 0, and of course dividing by 0 is impossible. Now there are cases where the denominator becomes 0 and you don't get a vertical asymptote, but if you have a vertical asymptote, that's because the denominator is 0 at that particular point. Well, if you look at -2x plus 4 equals 0, that's going to happen if x equals 2. So in terms of just the shifting, comparing this to y equals 1 over x, it's going to shift 2 units to the right and 3 units down. I didn't actually write this up in terms of shifts, but if I did write up in terms of shifts, there could actually be more going on. There can also be some distortion going on in terms of the overall shape. By that, the stretching and the shrinking, or possibly even a reflection about the y-axis can occur here. So none of that's going to be apparent from just this analysis. And to figure those things out, you need to plot some points and see what's going to happen. But it's going to have the two branches, be a hyperbola similar to y equals 1 over x. It'll have those two branches. The two branches are determined by the asymptotes. And then once you've got that figured out, then you can do some further point plotting to figure out exactly how it's going to work around those asymptotes. So let's go to GeoGebra. So I'll do a new share on the screen here and look at GeoGebra, which is, let's see, where's GeoGebra? Oh, there we go. Okay, so here's our GeoGebra, which you see the plots that I had up here before. I think I'll turn off the red curve. Maybe keep the green curve up there for right now to compare. And so we had here was, you see, 6x over negative 2x plus 4. So I'll put that in 6x over negative 2x plus 4. So y equals 6x divided by, parentheses, negative 2x plus 4, close the parentheses. And so what we can see is that it shifted the green curve, definitely. It looks like more than that's going on. It looks like we have a reflection either about the x-axis or the y-axis. And you could actually, I'm sure, set it up either way. A reflection about the y-axis means replacing x with its opposite. A reflection about the x-axis means replacing y with its opposite. And something has definitely reflected. And also looks like the shape's been changed in some other way also. So I would encourage you to go ahead and get some further understanding of that by looking at, actually, I guess we don't have to. GeoGebra did it for us. Oh no, that's not it. Okay, it's still down here. Okay, here it is. Okay. So yeah, this did some simplification. Y equals 6 times the quantity x over negative 2x plus 4. That's really the same as what I had. So yeah, for a second there, I thought maybe they had divided it out. No, I'll leave that for you to do to check that. If you were to divide it out, we can see some sort of reflection going on here. Anyway, the asymptotes, we already know that the vertical asymptote was at 2, which we can see here. And then the horizontal asymptote I claimed was at, what was it again? It was 6 divided by negative 2, so that was negative 3. Well, negative 3 is here between negative 2 and negative 4, which we can sort of see that also here. Now if we zoom out, if you zoom out far enough, the computer program has some problem with trying to create values. It's going up and down here. Has no trouble with plugging in the vertical things here and getting close to negative 3, though we can't actually see it from here. From here, it looks like it could just be the x-axis, but it's the vertical asymptote. The horizontal asymptote is actually y equals negative 3, as we saw before. And the horizontal asymptote occurred at 2. I'm sorry, vertical asymptote occurred at 2, but we, from here, can't really tell. It could be the y-axis. Have to zoom in a little bit. We start to see the gap there, and then once you see the gap, you can zoom in more and see better. Now, like many things in life, the advent of computers, the question becomes whether we need to know more math or less math to figure out how to work these things. And I'm going to say more math for the moment anyway. Of course, I have a kind of my own bias in that way. But yeah, you can see the asymptote of 2 here, the vertical asymptote, and the horizontal asymptote that way. Of course, if you zoom in too close to where those asymptotes come together, we start to lose the curve entirely. Anyway, that's probably enough information to think about for here, and we'll look at some future videos. In the future, we'll look at some more videos where we can go above and beyond this. So until next time, thanks for watching.